Okay, so here's our second video for day one. I have this here, but we're actually going to save this until next day, this first picture right here. Hopefully you may have gone to see this in a lab setting, but if you have a solenoid connected to an ammeter or a galvanometer and you move a magnet through it, you should see a current be produced. So we'll look at the details of the direction of that current coming up later. So we're going to just move on for now. Again, we'll come back to this. So if we scroll down, this is just to go over again our different right-hand rules. So when you have a wire, again, we already just saw this above, the general rule is that our thumb points in the direction of the current. So this is our current I, measured in amps, and our magnetic field is denoted by the direction that our fingers are curling around. So in this case, you can see it's going to travel in that direction. So in front of the wire, so it's going in front of that wire and then behind, and then in front and then behind. If you have a solenoid, we use, so let me just write that in. So this is B field. This is a vector. So if you have a solenoid, our thumb will represent the direction of the magnetic field, denoted by the symbol B, and our fingers tell us the direction of the current. And the next thing we're going to look at is when we have a moving charge. So again, for positive charges, just like conventional current, we're going to use our right hand. If you have a negative charge, you either just have to remember it's just everything gets flipped around, or you can just use your left hand. So the general rule for a positive charge moving through space in a magnetic field is our index finger will represent either, it could be the velocity if you have a single charge, or current if you have like lots of charge moving. Because remember, current, all it is moving charge. So our index finger, I for index, represents our current, or just our velocity of our single charge. Our middle finger represents our B field, our magnetic field, denoted by the symbol B. And our thumb represents a force. So what actually happens is if a charge passes through a magnetic field, a force results on the charge, causing it to change direction. So the charge will actually experience an acceleration. And a really cool application of this is the CRT TV. So again, it doesn't really matter anymore because we use LCD TVs, but this is very important for watching TV back in the days. This is the physics behind it. You had to deflect charge to create an image on a screen. So let's scroll down to see how this works. Okay. Actually, before we get into an example, this is, if you're really into math, you'll see what's called the cross product all the time. And basically, cross product is when you multiply two vectors. So you may remember that back in the days, like, you know, you've seen all these different ways. We have like, oh, A times B, it can also be written as A times B, or AB. Like, they all, from what you know in math class, those are all the same thing. But I'm going to tell you right now that it's actually a lie. So the x, when we have an x for multiplication, it's actually the cross product, and it's used when you multiply two vectors together. When you use a dot to represent that's called the dot product, and it's the multiplication of two scalars. So you can still use the x when you're multiplying two like single values together. But as soon as you get into three-dimensional space or two-dimensional space, you actually, the x and the dot mean different things. So what happens when you multiply two vectors together, it always results in a third vector that is perpendicular to the other two. So if you went back to, here's our right-hand rule, what we can see is that A and B are along a single plane. If you imagine like a 2D plane, that third vector, the multiplication of the two, is perpendicular to that plane. So if we have A cross B is up like this. One thing to note is A cross B does not equal to B cross A. because if you think about so A is our index finger, our first one is our index finger, then our middle finger. If you flipped around, B would become our index finger, A would be our middle finger, and we'd actually result in a arrow downwards. So B cross A would result in that third vector pointing downwards instead. So for this, here's our first equation we'll look at. So the equation for force experienced by a charge traveling through a magnetic field is given by F, here's force, is equal to the magnitude of the charge multiplied by V cross B. So yeah, X is for, X, like cross product, is for vectors. So Q is equal to V cross B. So again, how we represent that, let's say we have some velocity in this direction, and we have a magnetic field that is perpendicular to it. Again, this doesn't look 90 degrees, but I'm looking at drawing a perspective view of our three-dimensional space. Q cross B results in a force upwards. This is our force. The magnitude of the force would just be the velocity multiplied by the magnetic field multiplied by our charge. So here's our equations again. Force is QV cross B. Pretty much the same idea. If you have current in a wire, instead of QV cross B, it is the magnitude of the current multiplied by the length of the wire that is inside the magnetic field. So those are our two equations today. And it's not hard. Like the calculation is just multiplying three numbers together. What's difficult is then taking a step back and thinking about the directions of the velocity and the magnetic field and being able to figure out what direction is the force and what's going to happen. So let's scroll down to some examples. So here, this is going to put some in here. So for example, let's say we had a V in this direction. Oh, and before I forget, there's two ways to denote. Because three-dimensional space, we need to be able to recognize, like, we need a way of writing in and out of the page. So if you imagine an arrow, so here's a picture of, let's say, an arrow in like a 3D arrow. If you kind of want to change your perspective and looked at it straight on, it kind of just looks like a single dot and a circle around it. So this represents out of page. If we draw a circle with X, this means in to page. Okay, so that's just the notation that is used for three-dimensional space when drawn on two-dimensional paper. So here's an example to say we have a positive charge traveling to the left, and it's traveling through a magnetic field that is coming out of the page. What's going to happen? So we need to take our right hand and line things up. So first our index finger is going to point to the left, and then we need to get our middle finger to point at us, so out of the page. And then we look at what direction our thumb's pointing. We say, our thumb is pointing up. So the force that's going to be experienced is going to be straight up. Again, maybe I'll say, okay, let's say something is traveling into the page, and the force is downwards. Another question is, what direction must the magnetic field be? So we say, okay, my V is going to point into the page. So my index finger is going to point into the page, and I have to orient my right hand such that the thumb is pointing downwards. And we say, where's my middle finger pointing? It's pointing to the right. So my magnetic field is to the right. And I can draw it again. Here is my B field. Here's, if we have this is a three-dimensional picture. So the first two were two-dimensional pictures to show something moving in three-dimensional space. Here's I do a perspective drawing, VB. If this is a 3D picture, our force is going to be up. Here's our force. This is when Q is positive. However, if an electron was traveling, what we need to recognize that our force would be downwards when Q is negative. Okay. Again, two ways to do that. You just use the right-handed rule and say, oh, force is up. But if it's negative, it just goes down. Or if I do the exact same thing with my left hand, you'll notice that the force, the thumb, will point down. For some wire examples, same idea. Let's say we had L pointing downwards, so like the wire is traveling downwards and the current is traveling through that wire. And B field is to the left. Okay, our index finger line up with the wire, middle finger is B, and we see our force is going to be into the page as a result. Again, same idea. If I were to draw it in three-dimensional space, L, B, F would be up. This is for conventional current. If I was using electron flow, my force would be down. Here's an example. So I need to scroll down. Okay, so here's an example. So one thing we can recognize is that the I and B don't have to be exactly perpendicular. So if you have a current pointing up and a B going to the right, it's going to create a force. It's going to create a force. In this case, if you have a current going up, but you have a magnetic field like in such direction, again, this is 2D space, it's still going to create a force. In both cases, they're going to be into the page. However, assuming the magnitudes are the same, this force is going to be smaller. Okay, so you still create it, it's going to be smaller. If you have a current and the magnetic field's in the same direction, force is equal to 0. Okay, so what it comes down to is force is equal to QVB sine theta. So when you take math in university, well, if you take this type of math in university, you learn ways of writing vectors in three-dimensional space. So you don't actually need sine cos. It takes care of it. Like the process of the mathematical calculation will take care of it itself without sine cos. But we're not going to learn that right now. We can just use our trigonometric identities or sine, well, not identities, sorry, just trig functions, sine and cos. In this case, if we can see that, like in this one, we know that our sine curve, like something like that. If we can see that right here, when they are 90 degrees to each other, sine is at a maximum. So you get a maximum force. Over here, when they're 0 degrees from each other, we get that 0 force. Same as if it's 180 or 360, you get that maximum force. Same as over here again, right there. If you look at the first one again, if the magnetic field was 180 degrees in the direction, it'd just be, you'd also have that maximum force but in the opposite direction. When it's anywhere in between, we get some force that is, well, bigger than 0, but less than that maximum. Right? So like at 45 degrees, you're around there. So the force for the charge ends up being QVB sine theta, and same idea with a wire, ILB sine theta. And again, these are all in the formula sheet. And the tough thing is remembering what direction will the force be in.